We briefly talked about this map when we were talking about tight ice gradients and broad gradients. And I want to come back to this map because it's a good one. You might see that this map doesn't have wind speed on it, but it does have wind direction. And we had been talking about pressure gradient force as moving directly from high pressure to low pressure. And if that's the case, then we would expect that the pressure gradient force would move directly from an area like 1024 directly out to 1020, and it would be at right angles to our isobar lines. But that's not what you're seeing here. You're seeing directions of wind that are skewed a bit. And let's look at the low pressure as well. If you looked at a low pressure center, you might say that the wind should go directly from the higher pressure to the lower pressure, right along that line, right into the low pressure center. But when you look at these directions, they're not going that way. For instance, I could say, let's go from high pressure to low pressure and go directly in, but these lines are skewed. There's another force acting on these lines, and we're going to explore that a bit. These lines are not skewed by friction, because friction would be pulling back against the pressure gradient force and not changing the direction of the force. They will change the direction as much as it will go around surface friction, but not really changing it dramatically like this. There's another force that's taking place. Let's look into that. If you go back to Forrest Gump, you have to think about Newton's laws of motion and what's going on there, because the feather is going up and moving around, and so it's moving in vertical and horizontal directions. But underpinning all of that is the first law that says an object at rest tends to stay at rest. So the feather in his hand is going to stay in his hand. An object in motion tends to stay in motion. When he lets it go and the wind picks it up, it tends to stay in motion, unless there is a force opposing that motion. So let's think about that first law. Let's think about the second law, Newton's, just to extend it a little bit more. Newton's first law of motion, if you just look at the little golf ball, it's not going to move. Sorry. You have to exert force to make the golf ball move. And the second law is the law that you know that force equals mass times acceleration. And you can remember that by thinking, oh my goodness, there's so much mass in that elephant. You have to push him so hard and apply so much force to make him accelerate or move in a direction. That's what acceleration is. It is a speed in a direction. But there's a lot of mass there, so you have to apply a lot of force to get that to move. I want to talk to you a little bit about the force that's moving on that feather from Forrest Gump. And especially about acceleration, because acceleration is a vector that has speed and has direction. So for instance, the speed can increase or the speed can decrease and still be accelerating. So in physics, acceleration is increasing your speed or decreasing your speed. Acceleration is any change in speed. So I wanted to point that out to you. That is an acceleration and slowing down. Really important point. And also, you're accelerating when you change directions. When you keep the same velocity in your car, but you turn right, in physics, you are accelerating because you're changing the vector. You're changing the direction. This comes into play, obviously, with the feather and Forrest Gump. Let's go into it a bit more. That there are several forces going on that can change speed and direction, that can change speed going at 25 knots or at 15 knots, or change direction going north or going southwest or going southeast. Those are directions that can change with that feather. There are true forces acting on the feather, and then there are fake forces. Let's go into the true forces first. The true forces include things like the pressure gradient force, which we've been talking about. Also, we've been talking about friction that counteracts the pressure gradient force. There's one more, gravity. If you think about the feather in Forrest Gump, It's going down, it's going up, it's being impacted by a true force of gravity. Now, there's some other forces as well. They're fake forces. They're often known in physics as effects, not fake forces. Some people will call them that, but they're known as effects. The reason they are not true forces is because a true force impacts every part of the vector. It impacts the speed of the vector and the direction of the vector. So this effect in atmospheric science does not impact the speed of the vector. It only impacts the direction of the vector. And that kind of fits into what we were seeing on the map that was showing these directions skewed from high pressure to low pressure. So let's explore it a little bit more in terms of direction. These effects, these fake forces, because they do not have an impact on acceleration, they don't impact accelerating systems, but you will only find them in accelerating systems, in systems that are changing speed predominantly, some that are changing direction. Let's explore that a bit. For instance, you will find these fake effects in a car, in an airplane or a rocket, in an elevator. You'll see them on an amusement park ride, and in wings. Let's get specific. These forces that you know, a centrifugal force, a centripetal force, a G-force, they are not true forces because they act only on forces that are changing their acceleration. Let me explain. The one you know from every ride that you go on, just about every ride that you go on, is centrifugal force. And you know that when you go on the tilt-a-wheel, that you should not be able to be safe on that tilt-a-wheel because you should be falling right straight down the tilt-a-wheel, but you're not, because the centrifugal force that blasts your body in a different direction back, right? So as the tilt-a-wheel changes its acceleration and its velocity of its spin, you feel the difference in the direction vector pulling you back. And conversely, when the tilt-a-wheel slows down, you feel that back pressure go away. Pretty interesting. The centripetal force you know of when you take a sharp right in your car and everybody goes right. Everybody leans into the force. So when you take that sharp right in the car, you're changing your acceleration pattern by changing your direction. And you're also probably changing your speed there as well. And this force, centripetal force, does not change the speed of the car, but definitely changes your direction in the car. It's a force acting on an accelerating system. That's centripetal. G-forces are what you feel when your flight takes off and you're pulled back in the seat a bit. That's not a centrifugal force. A centrifugal force is a centered roundabout force around the center. A G-force just pulls you back. If you were an airline pilot and you were flying jets, you'd feel a G-force. If you get to be an astronaut, you definitely feel G-forces. If you scuba dive at all, you feel G-forces pressing down on you as you go down and increase your gravitational pull down as well. So that's where you see the guy being pulled back on a G-force. Happens on accelerating systems. Coriolis force is what we're going to be talking about. The Coriolis force is a fake force that has only recently been discussed. And I include this picture here because this is from World War I. And World War I, as you know, is the world war that really brought technology into war. And the Germans would launch off these huge artillery, and they would never hit their mark. And they didn't understand why they didn't hit their mark. But the French had figured out the Coriolis effect. It's named after a Frenchman, and we're going to explore it now and why they didn't hit their mark. Like I mentioned, it changes direction and not speed. We're going to get into that for the Coriolis effect. Oh, we'll get into that on the next video. See you then.